Hi everyone, in this video we are going to be checking out a very interesting paper related to KV cache, which is EpiCache, Episodic KV cache management for long-term conversation on resource-constrained environments. So the problem is, in terms of privacy, some companies, for example, they rely on large language models that work locally on their devices, for example, a smartphone or a computer. The issue is those devices, for example, mobile devices, have a limited memory, and sometimes the KV cache can actually grow beyond the size of the model itself. We are going to see that. This is the problem that this paper is attempting to solve, essentially to cap the maximum size of the KV cache without actually hurting performance. And by the way, there is going to be a Jupyter notebook related to this paper. It is very interesting. All right, let's see how it is. So they mention the KV cache grows linearly with the extended dialog history. So the more tokens you generate, KV cache actually increases, causing the model's memory footprint to quickly exceed device limits. Now, the EpiCache is a training-free KV cache management framework for long conversations in general, and it is under a fixed memory budget. In here, they mentioned that the system reduces latency and peak memory by up to 2.4 times and 3.7 times respectively. So let's go to a little bit of the introduction. So here they mentioned that existing systems, they tackle long conversation by summarizing the history. But the problem with that, such approaches rely on API calls to large language models and do not actually bound memory usage at inference time. So there is still a problem here. And they mention KV cache grows linearly with the context length. And this is an interesting fact that a multi-day dialogue between a user and an assistant, the KV cache of Llama 3.2 3 billion parameter model exceeds 7 gigabytes after just 30 sessions. Imagine that. In here they mention some approaches, for example, to KV management, for example, post prefill. We're going to see what it is, and also query dependent eviction. For example, looking at the history, and if there isn't any part of the history that is not related to the current query, you evict it, essentially to reduce the size of the KV cache. So to address the problems from earlier works, they propose EpiCache, which is training free KV cache management framework that enforces constant memory footprint through a block-wise prefill and episodic organization. These terms are important. We are going to see technically what they mean. Alright, so let's quickly jump to the background. I love the way that they technically define what a long conversation is. We formalize long conversation as answering a sequence of user queries, question 1 all the way to question NQ. NQ denotes the total number of queries. For example, this is the history. So let the history, dialog history, be represented as an order sequence of NU utterances. Okay, so this is the history. It is an order sequence of utterances. An utterance is a tuple that contains the speaker. It could be the assistant, or it could be the user, and also the text. So in here, given a long conversation H, an LLM encodes it into a key KV cache, which is KVH that we see here. For L layers and H number of KV heads, encoding N tokens produces L, which is for layers, H times N number of KV entries. Okay, so essentially mentioning how the KV cache grows. So what they are trying to do essentially is they want to find a smaller KV cache that is a subset of the full KV cache, and also without hurting performance. Okay, so when I jump in here, they mention for a query given the smaller KV cache, the generation of a large language model should be approximately same when you condition that query with the full KV cache. So let's quickly go into the framework itself. Let me quickly jump to this diagram. These are some approaches for managing KV cache. For example, there's post prefill eviction and block prefill eviction. In post prefill eviction, let's say you are generating a token, this token. So before generating it, let's say you have a for loop that gradually generates the KV entries. So it generates this KV entry, then this KV entry, then this KV entry, all the way to this. So it generates, let's say, 6 KV entries. And in the final step, you decode, you generate a token. So this is post prefill eviction. Post. So after generating the KV cache, in the decoding, you evict, you remove some of the tokens in the KV cache, essentially for management. So after doing that, you are left with this first and then the fourth KV entry. This is one approach for KV cache management. Another approach is block prefill eviction, which is actually related to this EpiCache. So it summarizes block by block depending on the block size. The model, for example, we have beginning, there's 1 KV entry, second KV entry, entry, then the third KV entry. So block size is 30. After generating 3 KV entries, you use a patch prompt. This is very important. This patch prompt is used as a query in the attention formula. That patch prompt assigns the KV entries, and the KV entries that achieve the highest attention are actually kept, and the ones that have low attention are actually deleted, are evicted. So in this case, when we go at this fourth step, the first and the third entry has been evicted. We're only left with this. We only keep one because the memory the memory size is 1. We just have one. We just want one entry for the KV cache. So that here it's written memory size of 1. If it was 2, for example, we'll keep the top 2 ones that achieve the highest attention. So if I jump in here, we have kept this. That's why it's green. In here, if we look at we generate 3 more entries. We apply a patch prompt. We look at all of the entries, KV entries. The one that achieved the highest attention is kept, and all other ones are evicted. And then here's the generation, the decoding step. Okay, so this is block prefill eviction. This is post prefill eviction. The most important part is this patch prompt, because KV cache relies on that. Okay, so here we have attention guided KV cache compression. So essentially what we discussed here, based on attention, you remove some and you leave some. Now let's look at the EpiCache. This is the core of the algorithm. So there are 3 stages essentially. The first stage is they look at the history, the entire history, and they divide it into multiple segments, and each segment is embedded and then projected onto a space. After projection, they apply clustering. So each cluster forms an episode. For example, this is episode 1, episode 2, episode 3, and each episode is essentially a separate topic of the history. So as you might imagine here, the history they are using here has 3 topics, and each episode, for example, this episode might be about hiking. So this is what they do first, and then for each episode they compute the centroid, and they do that by averaging the embeddings of all the segments, and then they find the segment that is closest to that particular centroid. That is the segment that they use as a patch prompt, and they use it in stage 2. So they pick that segment, then they move in a block prefill eviction, what we just saw from the beginning of the history to the end. They move gradually. So using attention, the segment becomes a query, and the part of the history in a block fashion is the key. And whenever a part of the history receives a high attention, it is appended to a KV cache of the episode that segment belongs to. That is why, for example, here to the end, it is the whole history, and if you notice, it is only part of the history that they pick to create the KV cache for that particular episode that segment belongs to. So that is why they call it episodic cache management. The cache depends on the episode. Similarly, they do the same for episode 2. In stage 3, which is actually important, let's say a person asks a question. Okay, they embed the question using cosine similarity. They find which episode actually that query is closest to, and they retrieve the KV cache of that particular episode to answer this particular question. For example, in here, the question the user asks which lens was the best for last hiking. In this case, they retrieve this second episode 1 KV cache. The LLM answers, and then this is the retrieval phase. After answering, that KV cache is actually updated with the current query, and if the cosine similarity between the query and all of the centroid of all of the episode is less than a threshold, a new episode is actually created. Let's see what it is technically speaking. By the way, there's going to be a Jupyter notebook where it is going to be much more clearer. So in here, maybe I can actually jump. So for example, in stage 1, this is how you define a segment. So a segment contains multiple utterances, and the total number of segments you have is k, which relies on total number of utterance, and W embed. W embed is the size of the segment which you select yourself. Technically, in stage 1, you create embeddings for each segment, which is EK, and after doing that, you cluster that embedding to create episodes, and when you combine all of the episodes, you should be able to get all of the segments. So this is a formula for each episode. This is how they compute the centroid, which is the average of all the embeddings of the segments, and then for each episode they compute centroid closest, essentially the segment that is closest to the centroid using cosine similarity, and the centroid closest segment is used as a patch prompt. This is very important. This is what they use in stage 2. So for each episode, we perform block prefill eviction over the entire context. So here at decoding time, each user query is embedded with the same encoder used in clustering. So they embed that query and they find the episode that query belongs to using cosine similarity, and for answering the question, they use the KV cache of that particular episode. So in here, when we go to stage 3B, when an episode KV cache is retrieved for decoding, the KV pairs generated at the current turn are appended to the retrieved episode cache. So essentially, this is an update phase to enrich the episode specific memory. At this stage, if the query embedding is not sufficiently similar to any of the centroids, EpiCache creates a new episode. All right, I think we are going to see Jupyter notebook and we'll be able to solidify the understanding in here. So here they mention EpiCache refreshes an episodic cache only when its size exceeds the budget, which is M plus M block. This is the size of the block, essentially a temporary processing. So the memory can actually reach the limit and you can consider the next block temporarily, and when that block actually part of the block receive a higher attention, you can delete part of the memory to put that block's higher attention entries into the current KV cache that you have. So this is more about sensitivity aware layer wise KV budget allocation. Quickly, let's look at the result for coin 3 4 billion, coin 3 8 billion using different benchmarks and also method. So here method, and these are the benchmarks. Let's see here the budget is 2,000 tokens. At the top, which is actually interesting, KV cache achieved the highest performance on this benchmark. KV cache did achieve the best performance, and notice that as the size of the budget increases, approaching full KV cache, they all converge to the same performance. Similarly here for the different benchmarks. So I'm going to skip to this part of the table 3, which is important. In here for Llama 3.2 8 billion parameter model, they compared EpiCache with full KV and full KV with prefix caching. So the setting is that after 30 days, when we have a history of 90,000 tokens followed by 300 queries, so the history contains 90,000 tokens. So they compared under this setting, and we have a memory budget of 8,000 tokens. So for full KV, it doesn't have stage 1. Right, it doesn't have embedding or clustering. It has a prefill section. So for each of the 300 new messages, each prefill takes 27.8 seconds. It doesn't have stage 3, so in total it takes this amount of time. And the peak memory 36.3, for example. And for the full KV with prefix caching, it doesn't have stage 1. It has stage 2, but you actually cache just once. So that is why we have times 1. So all of for the 300 messages, you just need to cache just once. So that's why we have 27.8 seconds times 1. But it has a decoding phase for each of the 300, and each decoding is 3.5 seconds. Similarly, actually this full KV also has the same decoding time. So the full KV prefix caching takes 36.3 seconds. Now EpiCache, it has embedding with this amount of time, clustering with this amount of time, prefill with this amount of time. So let's say we have 4 episodes, each take 18 seconds, and it has matching to get which episode that query belongs to get the episodic cache. Okay, it has the retrieval and writing back. It has also the decoding. For each of the 300 new messages, the decoding is 1.4 seconds. This is the total time, significantly less, and this is actually the most important part, 9.6 gigabytes, just proper for smartphones, for example, and laptops. All right, I think this is the core. We have seen the core of the paper. Feel free to check it out. Here they mention future work, for example, improving episode construction through more effective conversational embeddings, better embeddings, for example. They also mention evaluating EpiCache on more challenging benchmarks. Alright, so let's go to the Jupyter to see the implementation of the core ideas. So let's see EpiCache in action. So these are the stages that we had, stage 1 all the way to stage 3. I'm going to start by importing the libraries that we're going to be using. For example, sklearn for clustering, PCA essentially to reduce the dimensions of the embedding so that we're able to project them onto a 2D space. We'll also be using PyTorch, for example, for multiplications of the tensors. So in here, for example, the usual Hugging Face model, Quen. Alright, so in here, for example, this is the model that we're going to be using the usual Hugging Face stuff, right? This is the conversation tones. In here, this is the history. This is an utterance. This is an utterance, and multiple utterances, they form a segment. This is a segment all the way here. This is also a segment. Okay, so this is the formula that they use for dividing the history into multiple segments. K is the total number of segments that we have. So based on that, this is the function that does that. Let me actually print it. So for example, segment 0 contains multiple utterances, the user, and also this utterance, for example, is the user and the text. This is the second segment that we have. So next is to embed all of the segments and then cluster them to form the episode. And remember, when we combine all of the episode, we should be able to get all of the segments. So the idea is each segment becomes an embedding vector. K means then groups similar segments embeddings into episode. So for example, there's a camera like segment which forms an episode. There's a travel like segment topic in the history that forms its own episode. There's a PyTorch, maybe you have asked a question related to PyTorch, that part is also going to form its own segments. This is the embedding, and also K means for clustering. So for example, segment 0 and 1, they belong to this episode 30. Segment 2, 30 episode, they belong to episode 1. Segment 4, 5, they belong to episode 2. Now for each of the episode, we need to compute the centroid and also the centroid closest segment. Essentially, that centroid closest segment is going to be our patch prompt that is going to be used to create KV cache specific for that episode that segment belongs to. So here we have cosine similarity. So here, for example, for each of the episode, get the ID and then get the segments, average them to get the centroid, and store that information in the centroid dictionary in here, for example. And then for all of the segments, compute cosine similarity with the centroid to get similarities, and essentially get the patch prompt in here. Okay, so let's print that information. So for example, episode 1 has this segment. The patch prompt is actually going to be segment 3, which is this. Similarly for episode 2, episode 3. Now this is the part for clustering and also projection on a space. Let's actually do that. Segment 4, 5, they form a cluster, which is an episode 2. This is episode 3, this is episode 1. Now this also a function for the second stage, for the block prefill eviction. I don't want to go into this function, it will not make sense for me to explain them, but I have a nice diagram that explains block prefill eviction. These are some just helper functions for the simplified block prefill eviction function that I have here. So let's see how it works. Let's say this is the history: Nikon, camera, lens, PyTorch model, all the way to hotel. And let's say this is a patch prompt. So using this patch prompt under a memory budget of just 4 tokens, we are going to use block prefill eviction to create an episodic cache. Okay, so the block size is 3, which means that we move 3 tokens at a time in the history. So the first 3 tokens are Nikon, camera, lens. Here I write them, they are part of the KV cache. We can put them in the KV cache because that size is less than our memory, which is 4. In the second block, we take the second block. So we have considered the first block, which is this. In the second block, for example, the second block is model PyTorch training, which is actually this. So this is block 2. Since the total size of the memory is 4 tokens, we are actually only going to be able to keep 4 tokens. So using a form of attention, model has actually achieved a higher attention compared to PyTorch and training. And by the way, if part of the history, let's say lens, had received a significantly lower attention compared to, let's say, PyTorch and training, it will have been evicted and PyTorch, for example, will be inserted. So now we are still under budget, 4 tokens. Next, we look at the next 3 tokens which will form the next block. Using a form of attention, the KV is actually Nikon, camera, lens, model. It turns out that in this block, 50mm has received a higher attention compared to model. Model has been evicted and 50mm has been appended to our episodic cache. So we have 4 tokens now, and we are still under budget. At least we have not exceeded the budget. Finally, the KV cache is going to be Nikon, camera, lens, and 50mm. So let's see how a simple example here. So let's say we have a memory size of, let's say our budget is 60 tokens. So actually, let me print it. So what we are doing here is, in building episode 1 memory, the budget is 60. We look at the first 24 tokens in the history. They are the candidates. We keep all of them. Next, we look at another next 24. So in total, we have candidates of 48. So we keep all of them because they are under 60. Next, we look look at the next 24, so 24 plus 48, which is 72, but 72 has exceeded our budget, so we use the patch prompt, which is this, and an attention mechanism to only keep 60. Next, we need to look at the next 24, so 24 plus 60, which is 84, using attention and patch prompt to only keep 60. We look at the next 24 all the way to the end. So this is how the episodic cache is created. This is the same for episode 2, episode 3. After doing that, episode 1, for example, the representative prompt, the patch prompt is this. The compact memory part of the history that achieved a high attention is actually this. But technically speaking, by the way, the KV cache is a tensor, but here it's like a text, essentially for simplicity. Now let's look at the third stage. So we have this function that takes in a query. First, it encodes it, and then using cosine similarity, it finds which episode it belongs to, and it retrieves that episode KV cache. Okay, so let's print it. So for example, the query is this: for all of the episode, using cosine similarity, these are the similarities. The highest is episode 3. So in answering this question, the system should actually use the KV cache of episode 3. Similarly for one more query, similarly for one more query. In here, this is for answering a question using the retrieve episode. The query comes in, it is matched to get its memory, and a prompt is created, which is the memory in here, and also the query is embedded. By the way, this is for simplicity, but technically speaking, the KV cache is not like a text in here and you don't append it to a prompt. It is a tensor on itself for the large language model to generate more answers. So this is the tokenization, this is the model answering. Okay, here the query, it retrieved episode 3, and this is the answer based on the memory. Now let's look at the final part. Sometimes when you compute the cosine similarity between the query and all of the episode centroids, the cosine similarity might be very small, might be less than a threshold. In that case, you need to create a new episode. So that is what we have here. For example, this is equation, these are the cosine similarities between all of the episodes. They are all small, and using a threshold, since that all of them are smaller than the threshold, which means that we need to create a new episode. Okay, so this is EpiCache. All right, thank you for watching. I'll see you in the next video.